Welcome. There is nothing to do now but rest, and nowhere you need to be. Let your breathing slow. Let your shoulders sink into whatever is holding you. Tonight we drift through an idea vast enough to hold a star. High above the earth, the sun burns on, radiating about 380,000 trillion watts of power, every single moment, without pause, without asking anything of us at all. Earth catches only a sliver of that outpouring. Of everything the sun releases into space, our planet intercepts roughly 1/2 billionth of the total. The rest pours outward in every direction, unclaimed, unwitnessed, spreading through the dark for trillions of miles. Almost all of that light simply travels on forever, warming nothing, touched by no one. Inside the sun's core, mass itself is quietly disappearing. Roughly 4 million tons of matter convert into pure energy every second, vanishing from the sun's body and reappearing as light and heat. It happens continuously, deep in that furnace, far too small a loss for the sun to ever notice. Across a human lifetime, the sun loses more mass than every mountain on Earth combined. Nuclear fusion is the quiet engine behind all of it. Deep within the sun's core, hydrogen atoms are pressed together under crushing heat and pressure until they merge into helium. Each merger releases a small breath of energy, and trillions of these breaths, layered together, become sunlight. Every warm afternoon on Earth traces back to that one process, happening far beneath the surface we see. The sun has kept this rhythm for a very long time. For about 4.6 billion years, it has shone with remarkable steadiness, its light reaching planets, moons, and eventually the eyes of living things. Mountains rose and wore away, while the sun simply continued. It is older than almost everything we can see with our own eyes on Earth tonight. That steadiness will continue a while longer. The sun is expected to keep fusing hydrogen for roughly another 5 billion years before its nature begins to change. There is no rush in this. 5 billion years is longer than life has existed on Earth so far, a quiet stretch of time still waiting ahead of us, unhurried and enormous. Even a fraction of that solar output is almost impossible to grasp. The total energy the sun releases every second dwarfs everything humanity currently produces and uses combined, many times over. All our cities, engines, and lights together draw on a power source smaller than a heartbeat's worth of the sun's endless output. It humbles the scale of everything we have built. In 1960, a physicist named Dyson looked at this abundance and wondered what an advanced civilization might do with it. He suggested that any sufficiently developed intelligence would eventually want more energy than a single planet could ever offer. His idea was modest in tone, but enormous in scope, quietly reshaping how people have imagined the future ever since. Dyson published this thought in a scientific paper with a careful technical title. It was called Search for Artificial Stellar Sources of Infrared Radiation, a name far less poetic than the idea it carried. Beneath that dry heading lay a proposal that would later capture imaginations across generations, though Dyson himself framed it simply as a possibility worth searching for. At the heart of his proposal was a simple suggestion. Dyson believed that any civilization advanced enough and old enough would eventually need to capture nearly all of its star's energy output to sustain its growth. Not a fraction, not a convenient slice, but the whole outpouring of light a star has to give. It is a thought that stretches gently toward the edge of what engineering might one day become. Let your breath find its own pace now. No need to guide it. Notice the exhale growing a little longer than the inhale, a little looser each time. With every release, the shoulders settle further into whatever is holding them. There is no rhythm to keep except the one your body already knows. Let the next breath arrive on its own, unhurried, and the one after that too. Dyson never claimed the idea as fully his own. He credited its origin to a novel written decades earlier, Olaf Stapledon's Star Maker, published in 1937. Stapledon's book wandered across imagined galaxies and civilizations, and within its pages Dyson found a seed worth carrying forward. He simply gave old imagination a new scientific shape. Within that novel, stars themselves were imagined as harnessed. Stapledon described civilizations building structures around their suns, capturing starlight for their own use. It was fiction, written long before space travel existed, yet it held a vision of energy on a stellar scale. Dyson later admitted the image had stayed with him quietly for years before it became a scientific proposal. Curiously, the phrase Dyson sphere was never Dyson's own choice of words. Other scientists coined the term afterward, borrowing his name for a concept he had described quite differently. He had not proposed a sphere at all, not in the solid sense the name suggests. The label simply stuck, spreading further than his original wording ever did. What Dyson actually pictured was far looser. He imagined a wide, scattered swarm of collectors, drifting independently in orbit, rather than fused into one solid shell. Each piece would circle the sun on its own path, unconnected to its neighbors. It was closer to a slow, orbiting cloud than to any single enclosing surface. 4 years later, a different scale of ambition appeared. A Kardashev Type II civilization is defined simply as one that harnesses the entire energy output of its home star. Not a nation's worth of power, not a planet's, but a star's complete radiance turned to use. It marks a threshold far beyond anything humanity has approached. This threshold came from a Soviet astronomer named Nikolai Kardashev, who proposed the scale in 1964. He was searching for a way to classify civilizations by the raw energy they commanded, rather than by their technology or culture. His 3 simple tiers, planetary, stellar, and galactic, gave scientists a shared language for imagining advancement on a cosmic scale. Measured against that scale, humanity has quite a distance yet to travel. We remain well below even Type 1, the tier defined by harnessing all the energy striking a home planet. Our combined power use is a small fraction of what Earth already receives from the sun each day. It is a gentle reminder of how early we still are. To reach Type 2, the numbers grow almost beyond intuition. Such a civilization would be using roughly 10 to the 26th power watts of continuous energy, matching the sun's own total output. That is a number with little everyday meaning, only the sense of something vastly beyond planetary scale. It stands as the benchmark against which any Dyson-style project is measured. Yet building a solid version of this idea runs into an immediate problem. A complete rigid shell around the sun would demand far more material than exists in all the solar system's planets combined. Even gathering every planet, moon, and asteroid would fall short of the mass required. The arithmetic alone quietly rules out a solid sphere before engineering even begins. Jupiter, the largest planet orbiting the sun, still falls short of what a solid Dyson sphere would demand. Its mass, though enormous by any earthly measure, represents only a sliver of the material such a shell would require. Even if every asteroid, moon, and rocky world were added to it, the total would remain insufficient. The gas giant's bulk, impressive as it is, cannot answer this particular arithmetic. For a moment, let the mattress hold all of you. Feel your feet grow heavy first, sinking into the sheets as if made of sand. Let that heaviness climb upward, through your ankles, your knees, settling into your hips. Your arms follow, resting fuller against the bed. Even your head finds a deeper cradle in the pillow, drawn downward by its own weight. Nothing in you needs to lift itself tonight. Mercury, the smallest and innermost planet, offers a different kind of promise. Rather than building an entire shell, engineers have imagined dismantling this single world piece by piece. Its material, broken into panels and mirrors, could supply a meaningful portion of a partial swarm. It would not complete the vision alone, but it could begin one. That small world carries a mass of roughly 3.3 times 10 to the 23rd power kilograms. It is a number difficult to feel in any everyday sense, yet useful as a kind of measuring stick. Engineers use it to estimate how much raw material a single planet might contribute toward a swarm. Even one planet's worth of matter, in these terms, becomes a meaningful unit of cosmic accounting. A Dyson swarm takes a very different shape than a solid shell. Rather than one continuous surface, it consists of countless independent collectors, each following its own path around the star. Some might be broad mirrors, others thin panels of solar cells, drifting like a loose cloud of metal petals. Together they intercept only a fraction of the star's light each, but their combined harvest can still be vast. This design sidesteps a problem that troubles any rigid shell. A solid sphere would need to resist immense structural strain, stretched between gravity pulling inward and the star's own pressure pushing out. A swarm has no such burden. Each collector orbits freely, supported by nothing but the same physics that keeps planets in their paths. Because each collector orbits on its own, a swarm can grow without ever needing to be finished. New panels can be added one at a time, launched and set adrift whenever resources allow. There is no single moment of completion required, no full structure to assemble before any benefit begins. Even a handful of collectors already gathers some starlight, 1,000 more only extend the harvest. A Dyson bubble takes the swarm concept even further, removing orbit from the equation entirely. In its place are structures called statites, held aloft not by circling the star, but by the steady push of its own light. Instead of falling inward under gravity, a statit balances that pull against outward radiation pressure. It hovers, motionless relative to the star, wherever that balance holds true. Statites rely on solar sails, vast and thin, to catch enough starlight for this balance to work. The sail's surface must be large enough that the pressure of photons striking it can match the star's gravitational tug. Tilt the sail, and the balance shifts, letting the structure be nudged into a new stable position. It is less an object in orbit than an object held in place by light itself. For that balance to hold, a statit must be extraordinarily light for its size. Any added weight tips the scale toward gravity, and the structure begins to drift inward toward the star. Designers imagine materials thinner than foil, stretched taut across enormous areas, weighing almost nothing per section of surface. Such delicacy sounds fragile, yet in the vacuum of space, without wind or weather, it could remain steady for a very long time. A ring of collectors could circle a star along one single orbit, far simpler than any scattered swarm. Picture a slender band of panels, evenly spaced, tracing one steady path around the sun. Unlike a swarm spread through countless orbits, a ring lives in just one plane, one radius, one shared rhythm of motion. Its plainness makes it easier to model, and perhaps easier to build first, before anything grander follows. Only a modest slice of a star's light would ever reach a ring like this. A single orbital band, however wide, still leaves most of the surrounding sky untouched by any collector. Compared to a full swarm reaching toward every angle, a ring captures a narrow current within an ocean of radiance. Engineers often describe it as a useful beginning, not an ending point. Somewhere in the house, a low hum settles into the walls and fades. It might be a pipe, or the wind finding a gap in the frame, or simply the building easing under the weight of the night. The sound rises just enough to notice, then recedes again, like a tide pulling back from shore. Let it come and go without following it. Nothing needs your attention now, only the slow rise and fall of breath, matching the rise and fall of that far-off sound until both grow fainter, and further away and gone. Around a star, a solid, unbroken sphere could never settle into a stable orbit. Any slight shift in position would pull one side closer to the star's gravity, tipping the whole structure inward. Without countless independent orbits to hold it apart, the shell would drift, slowly at first, until it touched the star it was built to surround. It is one reason engineers stopped imagining a single continuous surface long ago. Most physicists now regard a full, rigid Dyson shell as structurally implausible. The forces required to keep such a surface from collapsing inward exceed what any known material could withstand. What once appeared in early illustrations as a smooth, solid globe has given way to looser, more forgiving designs. The swarm, not the shell, has become the shade most seriously discussed today. Tiny grains of rock, moving at tremendous speed, pose a slow but steady threat to any solid shell. Over centuries, countless micrometeorite impacts would pit and thin a continuous surface, grain by grain. A swarm can absorb such losses easily, since damage to one panel affects nothing beyond it. A single unbroken shell has no such forgiveness. Every scar accumulates on the same fragile skin. Heat and gravity would not press evenly across a solid shell's surface. The side facing the star bakes under direct radiation, while the far side cools in shadow, each expanding and contracting at a different rate. Tidal pull, stronger on the near side than the far, adds its own uneven strain. Across a structure so vast, these small differences compound into forces no single material could quietly absorb. Rather than one continuous surface, engineers now favor thousands of separate segmented panels. Each panel can flex, shift, and tilt on its own, absorbing stress without transmitting it to its neighbors. If one section is damaged, it can be replaced without disturbing the structures around it. The design trades the elegance of a single sphere for the resilience of countless smaller, cooperating pieces. Photovoltaic material remains the most discussed way to turn starlight into usable power across a swarm. Thin layers of light-sensitive material convert incoming photons directly into electrical current, much as solar panels do on Earth's rooftops. Scaled to the size of a collector fleet, the same basic principle could gather energy across an area far larger than any planet. Its simplicity of concept, if not of scale, is part of its appeal. Once gathered, that energy would need somewhere to go, and beamed transmission is one proposed answer. Some designs imagine focused microwave beams, carrying power across vast distances to wherever it is needed. Others favor laser-based transmission, tighter and more precise over interstellar spans. Either way, the energy would travel not through wires but through open space itself, arriving as light rather than current. Microwave beaming is one proposed way to send that collected power back down to Earth. A collector far out in space would convert sunlight into electricity, then into a focused microwave beam aimed at a receiving station on the ground. The beam would travel across empty distance, unbothered by clouds or nightfall. Engineers have already tested small versions of this idea between towers and balloons, long before anyone imagined it stretching across a solar system. Laser transmission offers another route for sending that same energy homeward. A tightly focused beam of light can travel farther with less spreading than microwaves, keeping more of its power intact across great distances. Engineers imagine such beams threading between collectors, relay stations, and receivers scattered through the solar system. The light would carry no sound, no warmth felt directly, only the patient arrival of power gathered somewhere far away. A swarm this size might never be built by human hands alone. Self-replicating robotic factories, once seated among the asteroids, could copy themselves again and again, each new machine building more collectors and more of its own kind. What begins as a handful of machines could, in principle, become millions. The idea borrows less from construction and more from growth, like a forest spreading outward from a single seed. Let warmth begin low, somewhere near your feet, a faint gathering heat like sunlight through a window. Let it rise slowly into your ankles, your calves, loosening whatever has been holding on there. Let it climb into your knees, your thighs, spreading wide and unhurried, the way heat moves through water left standing in the sun. Let it settle into your hips, your low back, wherever the day has left its weight. There is only this rising warmth, and the dark and the long, quiet room around you. Von Neumann probes take their name from a mathematician who first described machines capable of copying themselves. Sent to an asteroid, such a probe would mine raw material, build tools, and construct another probe identical to itself. Each new machine would repeat the process elsewhere, spreading outward through the belt, like something closer to biology than industry. The concept remains theoretical, but its logic is simple. Growth without limit, so long as material and energy allow it. Asteroids carry within them the very metals a swarm would need. Iron and nickel, common throughout the belt, could be extracted and shaped into structural frames, wiring, and support beams for countless collectors. Unlike planets, asteroids offer this material without a deep gravity well to fight against, making it easier to lift and move. What looks like scattered rubble from a distance may, in time, become the raw skeleton of an entire energy-gathering system. Solar sailing is no longer only a theory. In 2010, Japan's space agency launched a spacecraft named Icaros, unfurling a thin reflective sail in the vacuum beyond Earth. The sail caught sunlight the way a cloth catches wind, and the pressure of that light nudged the craft gently forward. It was a small, quiet proof that starlight itself could serve as propulsion, not just illumination. Icaros confirmed something physicists had long calculated but rarely observed directly. Sunlight carries enough pressure to move an object through space. Photons, though massless, transfer a faint push wherever they strike a surface. Over the sail's wide area, that faint push accumulated into a measurable change in the spacecraft's course. It was a small step, but it showed the same principle a Dyson swarm would rely upon, tested and working in real vacuum, under a real sun. Years later, the Planetary Society sent up a spacecraft called LightSail 2, orbiting closer to Earth than Icaros had traveled. Its sail, a shining square unfurled in low orbit, measurably raised its own altitude using nothing but sunlight's gentle pressure. The mission proved that solar sailing could work not just in theory, but as a repeatable, controllable technique. Each test brought the old idea of light as propulsion a little closer to practical use. Thin film photovoltaic material offers a promising shape for future orbital collectors. Unlike rigid solar panels, thin film can be rolled, folded, and unfurled across enormous areas without adding much mass. Its lightness matters enormously in space, where every extra kilogram costs fuel and time to launch. Spread wide enough, even a fragile-seeming sheet of this material could gather starlight across an area rivaling a small moon. Graphene enters these designs as a material almost impossibly thin and impossibly strong. A single layer of carbon atoms arranged in a honeycomb lattice can outperform steel many times over per unit of weight. Engineers imagining megastructure skins have pointed to graphene as a candidate worth studying closely. Its strength comes from the tightness of its atomic bonds, not from bulk or mass. A sheet you could barely see might still resist forces that would tear thicker materials apart. Carbon nanotubes carry a similar promise, but in thread-like form. Rolled into cylinders far thinner than a human hair, they exhibit tensile strength theorized to exceed nearly every other known fiber. Engineers have floated them as candidates for cables, tethers, and structural supports on a planetary scale. No factory yet produces them long enough or pure enough for such uses. Still, on paper, they remain one of the most compelling threads humanity has ever imagined weaving. No material available today could safely hold together a full, rigid, non-rotating shell around a star. The forces involved are almost impossible to convey in ordinary terms. Even the strongest known substances would strain and fracture under the imbalance of gravity and heat across such a structure. This is not a failure of ambition, but a boundary drawn by physics itself. Engineers studying the problem tend to set the solid shell aside and look instead toward lighter, more distributed designs. Rotating habitats offer a way around this problem for the people who might one day live among the collectors. Spun at a steady rate, a cylindrical structure can push its inhabitants outward against its inner wall, mimicking the pull of gravity. It is the same principle that presses you into a car seat during a turn. Within a swarm of collectors, these rotating habitats could drift independently, self-contained, each spinning its own small gravity into being. Somewhere below the reach of thought, a candle far off dims by slow degrees, its light growing smaller and smaller until it is only a memory of glow. You do not need to watch it go out. You only need to notice how unhurried the fading is, how little it asks of you. Let your own edges soften the same way. There is no task waiting at the end of this darkness, only rest, only the quiet settling of one more breath into the pillow. Housing large numbers of people within a swarm points naturally toward a design first sketched decades ago, the O'Neill cylinder. Picture two enormous rotating tubes lined with soil and rivers and small towns, sealed against the vacuum outside. Windows or mirrors could bring in sunlight already gathered by nearby collectors. Within a Dyson swarm, structures like these could serve as floating homes, threaded among the panels that harvest the star's endless output. Gerard O'Neill, a physicist working in the 1970s, drew up detailed plans for exactly this kind of colony. He imagined vast cylinders, spinning slowly in orbit, filled with farmland, forests, and neighborhoods under an artificial sky. His designs were meant for near-Earth space, not distant swarms, but the underlying logic carries over easily. A civilization gathering starlight at scale would likely need places for people to live among the machinery, and O'Neill's blueprints remain a starting point for that conversation. Energy gathered from a swarm need not stay near the collectors themselves. Some proposals imagine redirecting a portion of it toward terraforming projects elsewhere in the solar system, warming a cold moon, or powering machines that reshape a barren atmosphere. The same output that once simply escaped into space as sunlight could instead be aimed with purpose, transforming distant, silent worlds into places capable of holding life. Models built around these ideas suggest a completed swarm could gather energy vastly beyond anything humanity currently uses. Even capturing a small fraction of the sun's output would dwarf all the power plants, grids, and generators operating on Earth today, combined many times over. The numbers involved are difficult to hold in the mind. They describe not an upgrade to civilization's energy supply, but an entirely different scale of existence. Even a modest, partial swarm, built with technology reasonably extrapolated from today, would likely take centuries to assemble. Launch capacity, material supply, and construction logistics all impose limits that no single generation could overcome alone. Engineers who study this timeline speak less of finishing the project and more of beginning it, passing the work forward the way cathedral builders once did. Trusting hands not yet born to carry the effort onward. The largest barrier to any of this remains remarkably simple. It is the cost of lifting mass off the Earth and into orbit. Every kilogram sent upward demands enormous amounts of fuel, engineering, and money, long before it can be shaped into a collector or a habitat. Economists and engineers alike agree that launch cost, more than any theory, decides how far this dream can travel. Reusable rockets have already begun changing that equation. Falcon 9, built by SpaceX, returns its booster to Earth instead of discarding it in the ocean. Since 2015, this reuse has driven launch costs down by a wide margin year after year. What once seemed a fixed, unmovable price has proven surprisingly flexible under the right engineering. Newer vehicles aim higher still. Starship-class rockets are being designed to carry far more mass per launch than anything flown before. Their builders imagine hundreds of tons reaching orbit in a single flight, shrinking the number of trips needed to build anything ambitious. If that promise holds, the arithmetic of megastructure building changes considerably. Not every proposal for reaching orbit involves fire and fuel. Engineers have long imagined a space elevator, a structure tall enough to carry cargo from the ground straight into orbit along a fixed line. No engines, no explosive launch, just steady climbing. It remains theoretical, but it offers a strikingly different way to imagine bulk transport into space. Such an elevator would depend on a tether, unlike any material yet produced. Engineers describe it as a beanstalk, a cable strong enough to hold its own impossible length under tension. If fibers strong enough are ever manufactured, the energy needed to reach orbit could fall dramatically, turning launch from an explosive event into something closer to a slow mechanical climb. Let the muscles of your face loosen now, one by one. Let your jaw unclench, your lips part just slightly, the skin around your eyes settle without effort. Behind your closed eyelids, there is only a soft, shifting darkness, warm and undemanding. Let that darkness widen, spreading outward until it fills the whole of your resting mind, holding nothing, asking nothing, simply present as you drift. One promising shortcut avoids Earth altogether. In situ resource utilization means building with material already present near the construction site, rather than lifting everything from home. Asteroids and the Moon both carry metals and minerals that could become raw parts for panels, frames, and structures, cutting the need for constant supply trips across space. The asteroid belt, despite its vastness, holds surprisingly little material. Its total mass adds up to less than 4% of the Moon's mass, spread across countless scattered bodies. It is less a solid reservoir and more a thin scattering of rubble, drifting through a region wider than most people imagine. Ceres, the largest object in that belt, stands apart from its neighbors. Nearly round and rich in water ice alongside rock, it could serve as an early foothold for construction crews and robotic factories. Many mission planners see it as a natural first stop, a place substantial enough to support meaningful work before reaching farther out. Closer to home, the Moon offers its own promise. Its regolith, the fine dust and broken rock covering its surface, contains usable metals that engineers have studied for decades. Processing this material on-site could supply construction elements without a single additional launch from Earth, turning lunar dust itself into the beginnings of something built to last. Grander proposals push the idea further still. Rather than mining asteroids alone, some designs imagine disassembling entire planets, with Mercury named most often as the candidate. Its proximity to the Sun and modest size make it an appealing target on paper. Taking apart a whole world would supply enormous raw material, though the process itself remains almost impossible to picture at true scale. Pulling a planet apart demands more than clever engineering. The energy required must exceed the planet's own gravitational binding energy, the force holding every rock and layer together. Without surpassing that threshold, fragments simply fall back into place, drawn home by their own weight. It is a threshold measured not in machinery, but in raw physics. For Mercury specifically, that threshold has been estimated: Physicists place its gravitational binding energy near 1.8 times 10 to the 29 joules, a number almost impossible to hold in the mind. It dwarfs the output of every power plant humanity has ever built, combined across all of history. Any disassembly effort would need to summon energy on a scale the sun itself provides. Carrying out such mining would require more than human oversight. Coordinating thousands of extraction vehicles across a planet's surface calls for autonomous systems capable of adjusting instantly to shifting terrain and unpredictable debris. Human commands, delayed by distance and light speed lag, could never respond quickly enough. The work would belong largely to machines making their own decisions. Heat becomes its own quiet obstacle near a star. Collectors placed close to the sun would face temperatures far beyond anything found on Earth, threatening delicate materials and electronics. Engineers studying these designs treat thermal control as one of the hardest problems to solve, more demanding in some ways than the mining itself. So close to the sun, ordinary cooling methods fail entirely. There is no air to carry heat away, no water to circulate through pipes. Instead, structures would rely on radiative cooling, releasing heat directly into space as infrared light. Wide fins and dark surfaces, angled just so, would become as essential as the collectors themselves. Notice your breath wherever it happens to be right now. Not adjusting it, not counting it, only noticing. Each inhale arrives on its own, and each exhale leaves a little longer than the one before it. There is no destination for this breath to reach. It simply moves, the way tides move, the way orbits move, without needing permission from you at all. Distance changes what a collector needs to be. Nearer a star, even a small structure can intercept the same fraction of total energy that a much larger one would gather farther away. This means proximity offers a kind of efficiency, letting engineers imagine smaller, lighter collectors doing outsized work simply by standing closer to the source. Proximity brings its own complications, though. Objects orbiting nearer the sun must travel far faster to remain in stable paths, following orbital mechanics that grow stricter as gravity intensifies. Coordinating thousands of fast-moving collectors, each tracing its own tight loop, becomes a far more delicate task than arranging a slower swarm farther out. A single collector placed at Mercury's distance receives far more energy per unit area than one stationed near Earth. The difference is not subtle. Sunlight intensifies sharply the closer one travels toward its source, meaning fewer panels near Mercury could match the output of many more panels farther out, though at the cost of managing that fiercer heat. Certain proposals favor anchoring a Dyson swarm not randomly around the sun, but at its Lagrange points, 5 locations where gravity balances gravity. These pockets of stability exist because the pull of the sun and the pull of a planet, usually Earth or Jupiter, cancel each other in just the right way. A structure placed there tends to stay there, resisting drift without constant correction. Engineers see this as a natural scaffolding already built into the solar system's geometry. Lagrange points offer something rare in orbital mechanics: stillness within motion. Most objects circling a star must constantly adjust against drift, but these 5 points hold their position relative to 2 larger bodies without much correction needed. For swarm architects, this means fewer thrusters, less fuel, and less long-term maintenance. Anchoring collector arrays there could turn an unstable megaproject into something closer to a fixed installation, resting in a pocket the universe already prepared. Communications between the far-flung segments of a swarm would demand more than distance spanning transmitters. Each collector, moving on its own path, would need to send and receive signals through relay networks synchronized across enormous stretches of space. A message crossing the swarm might hop between dozens of nodes before reaching its destination. timing would matter as much as strength, since delays of even fractions of a second could scramble coordination across thousands of moving parts. Coordinating thousands of independent collectors resembles, in miniature, a problem humanity has already begun solving. Modern satellite constellations must track their neighbors, adjust their spacing, and avoid collision while maintaining coverage across the sky. A Dyson swarm would face the same challenge at an almost unimaginable scale, with far more units, far greater distances, and far higher stakes for any lapse in coordination. The logic, though, would not be entirely new. Starlink's constellation, with its thousands of satellites weaving careful paths above Earth, is often cited as an early, modest analog to swarm coordination. It is nothing like a Dyson swarm in scale or purpose, but it demonstrates something useful, that many independent objects can be tracked, adjusted, and kept from colliding using automated systems. Engineers imagining a future swarm sometimes point to this present-day network as proof that the coordination problem, while immense, is not unsolvable. A completed Dyson swarm, if ever built, would change how its star appears from far away. Outside observers would see less visible light escaping into the galaxy, since collectors intercepting sunlight would leave less of it to travel onward, unimpeded. The star itself would remain unchanged at its core, still fusing hydrogen as always. Only its outward brightness, as measured from a distant vantage point, would seem quietly diminished. Astronomers searching the sky for possible megastructures look for exactly this kind of dimming, paired with an unusual signature in infrared light. A star behaving strangely, radiating more heat than its visible brightness would predict, becomes a candidate worth studying. No proof of artificial construction has ever emerged from these searches. Still, the method itself, comparing visible and infrared output, remains a real and ongoing tool in the search for distant technology. Let the weight of your body settle now, piece by piece. Feel your feet grow heavy first, sinking into the mattress as if gravity had doubled just for them. Let that heaviness climb slowly upward through your calves, your knees resting fully into whatever is holding you. Your hips grow heavy next, then your back, pressed and supported all at once. Let your shoulders drop their weight completely, and your arms turn to something soft and unmovable. Even your head, resting where it lies, needs nothing more from you than to be heavy and held. Waste heat is unavoidable in any system that captures and uses energy on a massive scale. A civilization harvesting a meaningful fraction of a star's output would inevitably lose some of that energy as heat, radiating outward not as visible light, but as infrared. This is simple thermodynamics, not speculation. Any structure doing useful work around a star would glow faintly in wavelengths invisible to the human eye, betraying its presence to instruments built to notice. This excess infrared glow forms the entire basis of the search strategy Freeman Dyson first proposed back in 1960. Rather than looking for radio signals or flashing lights, astronomers scan the sky for stars radiating more heat than their visible brightness explains. It is a patient method, built on physics rather than hope, searching not for a message, but for a byproduct, the unavoidable exhaust of any civilization vast enough to harness its own star. A survey called the Jhat Project once turned its attention outward, scanning thousands of distant galaxies for a particular kind of glow. Rather than searching star by star, its designers reasoned on a grander scale, looking for entire galaxies radiating more infrared light than natural processes could explain. If a civilization somewhere had wrapped countless stars in collectors, the whole galaxy might shine strangely warm. The search was patient, wide, and thorough. The name Jhat stands for Glimpsing Heat from Alien Technologies, a project built on data gathered by the WISE Space Telescope. WISE had already mapped the infrared sky in extraordinary detail, cataloging heat signatures across the heavens for other purposes entirely. Researchers repurposed that archive, sifting through it for anomalies. It was less a new telescope than a new way of looking at what had already been quietly recorded. Despite the scope of these efforts, no confirmed Dyson sphere candidate has ever emerged. Thousands of galaxies, thousands of stars, examined carefully for the telltale infrared excess, and still nothing has matched the signature with certainty. This absence is not failure. It is simply the honest result of a real search, conducted with real instruments across a very large and very quiet sky. One star did draw unusual attention. Known formally as KIC 8462852 and more casually as Tabby's star, it dimmed in strange irregular patterns that puzzled astronomers. The dimming did not match the steady rhythm expected from an orbiting planet. For a while, the possibility of an artificial structure passing before the star felt genuinely worth considering. Further observation offered a calmer explanation. The dimming of Tabby's star is now most often attributed to clouds of orbiting dust, remnants perhaps of a shattered comet or a slow collision long ago. Nature, it turned out, had its own ways of dimming starlight unevenly. The mystery did not vanish, but it settled into something ordinary and familiar. Astronomers have proposed another method worth mentioning, one built on the shape of a star's dimming during a transit. A planet crossing in front of a star produces a smooth, symmetrical dip in brightness. An artificial structure, angular or irregular, might instead leave a lopsided or jagged trace in the light curve. The shape of the dip itself becomes a kind of fingerprint. Some searches have turned toward smaller, dimmer stars called white dwarfs, where a Dyson sphere's signature might stand out more clearly. A white dwarf is faint and compact, its natural light output modest and easy to characterize. Against that quiet backdrop, even a small orbiting structure could cast a noticeable shadow. The stillness of the star makes the search a little easier, because a white dwarf is so much smaller than a sun-like star. Any Dyson sphere built around one would need to be far smaller as well. The scale of the structure follows the scale of its star. A sphere sized for our sun would dwarf a white dwarf entirely, while a modest shell might comfortably encircle one. Proportion, even here, remains the guiding rule. Somewhere far off, a sound arrives that you cannot quite name. Perhaps it is wind finding a gap in a window frame. Perhaps it is a house settling into its own old bones, a low creak somewhere in the dark. It comes, it holds a moment, and then it fades again into the wider hush. You do not need to trace where it came from. It only passes through the room, the way a tide passes over sand, leaving everything a little more still than before. Breakthrough, listen, one of the largest modern efforts in the search for extraterrestrial intelligence, has folded megastructure detection into its broader mission. Alongside listening for radio signals, its instruments also watch for the kind of infrared excess a Dyson sphere might produce. The project treats both possibilities as worth pursuing, radio whispers and thermal glows alike. It is one more patient set of eyes turned toward the same enduring question. Fermi's paradox asks a simple thing: if the universe is old and vast, where is everyone? Some apply that same question to megastructures. If advanced civilizations exist, why do we see no completed spheres, no swarms dimming distant stars? The silence itself becomes a kind of data point, though a faint and uncertain one. Finding no Dyson spheres does not prove they are absent. It only offers a weak boundary on how common advanced civilizations might be. Our surveys are limited, our telescopes young, our search radius a small bubble within a much larger dark. Absence of evidence here is treated gently as a hint rather than a verdict. Not every thinker believes advanced life would even want a Dyson sphere. Efficiency, some argue, might make such vast collectors unnecessary. A civilization skilled enough to build one might also learn to need far less energy per achievement. Growth, in this view, could bend inward rather than sprawling outward across a star. Other visions turn away from raw energy collection entirely, toward pure computation instead. Rather than harvesting light for power alone, an advanced mind might build outward to think. This idea imagines shells not as solar panels, but as vast layered processors circling a star like nested lanterns. Such a structure is called a matryoshka brain, named for the nesting dolls it resembles. Layer after layer surrounds the star, each one running on the waste heat cast off by the layer before it. Energy cascades outward, shell to shell, growing cooler and slower as it travels, until it finally escapes as faint warmth into the dark. Each nested shell offers the next a second chance to use energy already spent once before. Heat that would simply radiate away instead gets caught, processed, and passed further out. In principle, this recycling could squeeze far more use from a single star's output than any single flat collector ever could. The outermost shells, by this reasoning, would run cooler than the ones near the star. Lower energy allows lower temperatures, and lower temperatures allow more delicate, more efficient processing. The architecture mirrors something like a mind cooling, as its thoughts spread outward from a busy, warm center. The idea reached wide audiences through physicist Robert Bradbury, who developed and popularized the matryoshka brain concept during the 1990s. He drew together earlier threads of megastructure, thinking, and computation theory into one imagined design. His writing gave the concept its now familiar name and its careful, layered logic. A completed Dyson swarm, spread wide enough, could offer more total collecting surface than every planet in the solar system combined. Millions of individual panels, spread across countless orbits, add their small areas together into something immense. The sum becomes larger than any single world could ever provide on its own. Let warmth begin somewhere quiet now, perhaps low in your chest, a small, steady glow settling in. Let it spread outward from there, unhurried, reaching your shoulders, loosening what has been held too tightly all day. Feel it move down through your arms, into your hands, until your fingers rest heavy and still. Let it drift lower, too, through your stomach, your hips, down each leg, all the way to your feet. Wherever this warmth travels, let it stay a while, easing you further into the mattress beneath you. Estimates suggest that capturing just 10% of the sun's output could power projects on an interstellar scale. That fraction alone would dwarf every energy source humanity has ever built or burned. Such a share, directed with purpose, could drive machines far beyond anything now in orbit. The numbers involved are almost impossible to hold in mind, yet they follow simply from how much the sun already gives. Directed energy propulsion is one proposed use for a swarm's abundant power, pushing starships forward with focused beams instead of fuel. Engineers imagine vast arrays of lasers, drawing on collected sunlight, aimed at distant sails. A ship needs no propellant if the push comes from outside itself. The concept turns stored starlight into motion across the dark between stars. Breakthrough Starshot offers a small working sketch of this larger dream, proposing laser-driven sails no bigger than a postage stamp. Ground-based lasers, not orbital swarms, would push these tiny craft toward nearby stars. It remains a modest first step built with today's materials and today's budgets. Yet it hints at what a sun-powered array might one day accomplish at a far grander scale. A Dyson swarm could theoretically power a laser array the size of a planet, built for sending messages across interstellar distances. Such a beam would need to stay coherent over trillions of kilometers, carrying signal instead of noise. The energy required for that kind of clarity is immense. A swarm's endless supply of sunlight could, in principle, sustain it without strain. A swarm's surplus energy might also enable research into exotic propulsion, ideas that remain unconfirmed by physics as it stands today. Warp concepts and other speculative drives demand energies so vast they dwarf anything achievable now. Access to a star's full output could, some suggest, finally make such experiments possible. Whether the physics itself allows, it is still an open question, unresolved and unproven. Before any swarm could rise around the sun, a stable base beyond Earth would likely need to exist first. A lunar factory, built from local materials, could supply the earliest raw components. Everything launched from Earth costs enormous energy, but material mined and shaped on the Moon costs far less to send onward. This modest foundation may be the quiet starting point for something much larger. Engineers who study megastructures keep returning to the same requirement: build small before building vast. A base on the Moon or among the asteroids would supply metal, glass, and rare elements without the cost of launching them from Earth's gravity well. Every kilogram lifted from a planet's surface demands fuel, heat, and risk, while material gathered in space simply drifts toward its next use. This is why so many proposals begin not with mirrors or panels, but with mining equipment and modest refineries. The dream of a sphere around the sun rests, for now, on far humbler machinery. Many feasibility studies treat an off-world industrial base as a necessary early milestone, something to build before anything larger becomes possible. Whether on the Moon or scattered across asteroids, this base would need to mine, refine, and manufacture without depending on supplies from Earth. Such independence, once achieved, would mark a turning point. Only then could construction reach beyond what Earth alone could ever support. Some architects of these ideas propose beginning small, with a modest demonstration array placed near Earth before anything vast is attempted. A single ring of panels, easily monitored and repaired, would prove the basic method's work. Confidence, once earned at this scale, could justify expansion outward. It is a careful first step, built to be understood before it is multiplied. A phased approach could see the swarm's density thicken slowly, generation by generation, rather than arriving all at once. Each new ring of collectors would build upon what came before it, adding coverage without overwhelming the systems meant to manage it. Time, in this vision, becomes an ally rather than an obstacle. What begins as a scattering of panels might, over centuries, become something vast and continuous. Space-based solar power stations, already studied by agencies such as Japan's JAXA, stand as early real prototypes of this much larger idea. These stations would collect sunlight in orbit and beam the energy down to Earth, well beyond what ground panels alone can gather. Though modest in scale, they test the very principles a future swarm would depend upon. Each small experiment today is a quiet rehearsal for something far greater. In Japan, engineers at the space agency JAXA have already tested small versions of this idea, sending microwave energy from an aircraft down to a receiver on the ground. It was a modest experiment, measured in kilowatts rather than the vast scales imagined for a swarm, yet the physics held. Energy crossed empty air and arrived usable, proving a fragment of the concept works today. China has proposed its own orbital solar power station, a real engineering plan rather than a thought experiment. The design would gather sunlight far above the atmosphere and send that energy down through wireless transmission. It remains years from completion, and its scale is nowhere near a swarm. Still, it stands as a genuine step toward large-scale energy collection beyond Earth's surface. Money, more than imagination, may end up building the first pieces of a future swarm. Space-based solar power promises energy without weather, clouds, or nightfall, and that promise alone can justify investment long before anyone speaks of Dyson spheres. Infrastructure built to profit from orbital energy today could, decades later, become the scaffolding for something far larger. Ambition, in this case, follows economics rather than leading it. Theorists working on this idea argue a full sphere may never be necessary at all. If a partial swarm captures enough energy to satisfy a civilization's needs, there may be no reason to expand further. Growth, after all, tends to stop once demand is met. A finished shell, in this view, is less a destination than an unneeded extreme few would ever choose to build. The word megastructure covers far more ground than any single design. Dyson spheres belong to this family, alongside ring worlds, orbital habitats, and other constructions vast enough to reshape how a civilization relates to its star or planet. Each concept imagines matter organized on a scale beyond anything built by hand. The term simply gathers these dreams under one shared roof of possibility. Freeman Dyson himself, in later years, admitted his doubts about the solid shell that carried his name. He never believed a rigid sphere was the most sensible design for capturing a star's energy. Loose collectors, scattered and independent, made far more engineering sense to him. The idea people remember most vividly, it turned out, was not the one its own author most trusted. Dyson later expressed genuine surprise at how his proposal was remembered. He had described a loose swarm of independent collectors, yet the public imagination reshaped it into a solid, continuous sphere. He found the shift a little amusing, noting that the version everyone pictured was never the one he had written. Ideas, once released, often take shapes their creators never intended. Long before physics caught up with fiction, the author Bob Shaw imagined something similar in his novel Orbitsville. Rather than a solid ball around a star, he wrote of an enormous ring-like shell, vast enough to hold entire worlds within its curve. His creation gave millions of readers a tangible, dreamlike picture of megastructures decades before the science community seriously debated their feasibility. In the strategy game Stellaris, players can research and construct a Dyson sphere as one of the final achievements of their civilization. It appears near the end of the technology tree, a visual reward for reaching the furthest edge of progress. For many players, this glowing structure became their first real introduction to the concept, long before they encountered Dyson's original paper. Star Trek once devoted an entire episode to a solid Dyson sphere, its crew discovering an enormous artificial shell wrapped completely around a star. The image was striking, smooth, and impossibly vast, exactly the kind of solid structure physicists now consider unlikely. Still, that single episode shaped how an entire generation first pictured the concept, long before the science was widely explained. The jaw loosens first, releasing whatever it was holding. Let it hang, unclenched, heavy as wet clay. The muscles around your eyes give way next, the small tension behind the brow finally letting go. Behind closed eyes, there is only a warm, shifting dark, no shapes to follow, no edges to track. Let your face become unreadable, undefended, simply resting on the pillow the way it was always meant to. Popular culture often blends Dyson's original swarm idea into something he never proposed, a solid, impossible shell. Films, games, and novels tend to favor the smooth, continuous sphere because it reads more dramatically on screen than scattered panels. The engineering reality, loose and modular, rarely photographs as well as a glowing, perfect ball. So the myth persists, borrowed and repeated, long after physicists explained why the solid version cannot hold together. Certain theoretical designs propose partial shells covering only specific latitude bands around a star, rather than the whole surface. These band-like structures would ring the star like a wide belt, leaving the poles open and unobstructed. Such a design avoids some of the structural stress that a complete shell would face, while still capturing a meaningful share of stellar energy. It is a compromise between ambition and physical possibility. A Dyson bubble held aloft by statites could prove more stable over long time scales than a solid rotating shell ever would. Because each statite balances gravity against light pressure independently, there is no single rigid structure to strain or crack. The whole arrangement can flex, drift slightly, and correct itself without one failure threatening the rest. Stability in this design comes not from strength but from independence. Orbital resonance among thousands of swarm collectors could, over long timescales, nudge some of them into overlapping paths and eventual collisions. Small gravitational tugs between neighboring orbits accumulate slowly, the way a faint rhythm builds into a stronger beat. Left uncorrected, these tiny nudges could eventually send collectors drifting toward one another. It is a subtle problem, born from the patient arithmetic of gravity across centuries. Simulations of large-scale swarms suggest that active traffic management would be essential to keep so many collectors from drifting into each other. Automated systems would need to track thousands of independent trajectories continuously, adjusting tiny thrusts to maintain safe spacing. The scale resembles air traffic control, except stretched across millions of kilometers and countless moving parts. Even a slow, careful system would need to work without pause. Self-repairing swarm elements, equipped with small built-in robotic systems, are proposed as one answer to inevitable wear and damage. Rather than waiting for human intervention, each unit could carry tiny machines capable of patching micrometeorite punctures or replacing worn joints. Over centuries, this kind of built-in resilience could keep a swarm functioning long after its original builders moved on to other projects. Maintenance in this vision becomes part of the structure itself. Radiation damage to photovoltaic materials remains a long-term concern, since centuries of steady exposure gradually degrade even the sturdiest solar cells. Cosmic rays and intense stellar particles slowly alter the crystal structures inside collectors, lowering their efficiency year after year. What begins as a barely noticeable dimming compounds across decades, eventually leaving whole sections far less productive than they once were. Even starlight, given enough time, leaves its mark. Redundant modular design offers a practical answer to this slow decay, allowing degraded collectors to be swapped out gradually without halting the whole system. Each unit exists as one replaceable piece among countless others, never critical on its own. New panels could be added as old ones are retired, keeping the swarm's total output steady across generations. The structure in this sense is never finished, only continuously renewed. Researchers working through the engineering math estimate that building a full Dyson swarm, even with heavy automation, could take thousands of years. The sheer number of individual units required, numbering in the trillions, sets a hard limit on how quickly any civilization could assemble them. Automation helps enormously, but raw material transport and construction logistics still demand time measured in generations upon generations. Some undertakings, it seems, simply outlast the builders who begin them. Exponential growth changes the arithmetic of construction entirely. If each factory can build not just collectors but copies of itself, the total number of units no longer grows in a straight line but doubles again and again. A handful of replicating machines could, in theory, become millions within a handful of generations. Under this model, timelines once measured in millennia might compress into mere centuries. Let your breath find its own rhythm now, without any need to guide it. Notice the exhale growing a little longer than the inhale, the way a wave draws back further than it arrives. Each breath out can carry a little more of the day's weight with it, leaving your shoulders looser than before. There is no place this breath needs to reach. It simply keeps unfolding, one long, easy release after another. A civilization capable of raising a swarm around its entire star would almost certainly have already mastered movement between worlds. Ferrying trillions of components from mines to orbit demands routine, reliable transport on a scale far beyond anything humanity has built. Fleets of automated freighters would need to cross interplanetary distances as casually as ships cross oceans today. Swarm building in this light looks less like a single project and more like the natural extension of an already mobile species. One proposal skips mining altogether and turns instead to the star itself as a source of raw material. This idea, known as starlifting, imagines drawing matter directly from the sun's outer layers, rather than digging it from planets or moons. Instead of dismantling worlds, a civilization might simply borrow from its star's endless surplus. The sun, after all, holds far more mass than any planet could ever offer. Starlifting works, in theory, by using powerful magnetic fields to pull plasma away from a star's outer surface. Charged particles, already loosely held at the edge of the star, could be guided along magnetic channels into waiting collectors. Once gathered, that plasma could serve as raw material for construction or as fuel for other processes. The star becomes less a fixed body and more an active resource, tapped rather than merely observed. Removing mass from a star carries an unexpected benefit. It could extend how long that star burns steadily. A lighter star fuses hydrogen more slowly, stretching out its stable years rather than shortening them. In effect, careful starlifting might let a civilization dial down its star's aging process, buying itself far more time beneath a familiar sky. It is a strange kind of gardening, tending a flame by gently thinning its fuel. Pairing starlifting with swarm construction appears often in speculative engineering discussions, since the two ideas complement each other so neatly. Material drawn from the star could feed the very factories building collectors meant to harvest that star's light. Energy and matter, in this vision, both originate from the same source, closing an elegant loop. Whether such synergy could ever work at scale remains an open question, but its logic keeps drawing thinkers back to it. For all its careful math and layered proposals, a full-scale Dyson sphere remains firmly speculative engineering, not something within reach of any near-term plan. Every version, from solid shells to loose swarms, depends on technologies and industrial scales humanity has yet to develop. It exists today as a thought experiment stretched across centuries of imagined progress. The idea persists not because it is close, but because it is coherent enough to keep exploring. Cosmologists occasionally speculate that structures resembling Dyson spheres might not be optional for long-lived civilizations, but eventually necessary. As stars age and change, species that stay tied to their original conditions may find their worlds no longer hospitable. Harvesting and redirecting a star's energy could become less an ambition and more a survival strategy. No one yet knows whether life elsewhere has ever faced or solved that particular problem. Millions of years from now, the sun will swell into a red giant, its outer layers reaching outward toward the orbits of the inner planets. Any structures built too close would need to retreat long before that expansion arrived. A swarm, unlike a fixed world, offers a rare kind of flexibility. Its pieces could be nudged outward, orbit by orbit, following the habitable warmth as it shifts. Even a star's slow transformation might be something a civilization could simply move alongside. The idea of building a Dyson sphere indoors, decades after it was first written down, as a benchmark for how far human ambition can reach when measured against the light of a single star. It is not a blueprint waiting to be built, but a kind of measuring stick, a way to ask how much energy, ingenuity, and time a civilization might one day command. Each version of the idea, from solid shells to drifting swarms, still points toward the same quiet truth that starlight unclaimed above us tonight holds more than enough for every dream we have yet to dream.